interaction, number of Landau levels which are allowed to mix with the lowest 3 Landau levels. In fact, for most of our numerical computations, we used 6 Landau levels, and lowest 3 and another 3, but we checked that it does not change even if you include more. With system size, with changes in the value of the Zeeman energy. We also saw that if you used restricted Hartree-Fock, where we do not allow for spin mixing at the edges, then what happens is that you actually get the crossing of the edges. It is not an avoided crossing, because it is actually a crossing at the edges, and only when you spin unrestricted, these crossings actually become avoided crossings. But you can see the spin switching, the mode switching even in unrestricted Hartree-Fock. We also did since there is one problem, exact diagonalization in these kinds of systems is beyond reach even for small systems. So, we did not even attempt that. But one limitation of Hartree-Fock is that the ground state can only be a Slater determinant of single particle states. So, at t is equal to 0, the occupation of each state has to be 0 or 1. But allow for intermediate occupancies, we used a variational ansatz. We used a class of variational states that do not conserve particle number. For instance, we took a Slater determinant in our case, which is a combination of 0, 1, 2 and 3 fillings. And in fact, we checked that when we used it for just the nu is equal to 1 with 0 and 1, it gave pretty good answers close to the exact ground state. But unfortunately, here for us, we found that we could get non-arbitrary values of occupation number by changing relative values of exchange and direct interaction, as long as the exchange was a small percentage of the direct interaction, that is the Fock, this is the Fock and this is the Hartree term, then one could get things like this. But once the exchange term became greater than 0.6, the direct term, and in real Coulomb of course they are the same, then we got back nk 0 or 1. We are interpreting this to say that the Hartree-Fock solution is actually quite stable. It is not easy to move away from it. So, this is the results that we have got, and now I will describe some kind of experimental scenarios that one can think of, where you could try to see whether you can get this kind of stuff.
So, essentially, since it does not depend too much on Q naught, essentially saying screening is not that important.
Screening is not that important. You can get it even for 0 screening.
I'm just wondering, because if you, for example, look at Ando's work or others, where they calculate G factor as a function in the bulk, not in the edge. There's some more screening seems to be important, because whether you are at some age of Landau level or something, the G factor goes up and down. So somehow the age you are saying is making screening less and less relevant.
Yeah, and you are talking about the G factor changing, that is in graphene, right? Not in.
But there's some older work of Ando's on MOSFET, basically.
There also the G changes drastically.
Yeah, and that is mainly because they broaden it by a density of states.
I see.
If you are at the edge of the spectrum, then the screening goes to 0 and somehow that shoots up.
I see.
But that's not
a yeah. Yeah.
Okay. Also, that's a bulk calculation.
That's a bulk calculation on all the edge. Yeah. So, what are the possible experimental signatures for such thing? So, one thing is that you could have signatures in spin transport. You could consider making a quantum point contact by applying a gate voltage to make a constriction, and these kinds of things are possible, that you can tune it to a conductance of 2e squared by h. So, that 2 modes are conducting and one of the modes is backscattered. So, such a sample can be made. The quantum point contact region, for the region that we are looking at, you actually have the QPC region has to have bulk spin polarization, because it has been shown that you would actually get, it gets polarized, it does not remain 0 up, 0 down, it gets polarized for EC is greater than 2.13. So
one mode gets backscattered simply because it pinches the right and the left moving down close to each other.
What?
One mode gets backscattered because
yeah.
its right and left movers get close to each other.
No, one of them gets backscattered because you've pinched it off.
Right. So
yeah, with this quantum point contact. Yeah. So that way they can control by this pinching they can control they can use 3, 2, 1, 0, anything that they want. But because these things are polarized, what you need to do is that even if all 4 of them are phase A, that is the ordering is just 0 up, 0 down and 1 up, then you need to have they need to rotate in this region, because here you need to have them to be 0 up, 1 up. But point is that if you now you put the source on the top left and the drain on the top right, polarized nu is equal to 2 implies that the middle and inner modes have to undergo spin rotation in the quantum point contact region. And so if all edge phases are in phase A, then the incoming and the outgoing currents are unpolarized, because the incoming current is this up and down, outgoing current is also up and down, so it remains spin unpolarized. But if I change the slope on one side to make them phase C, what you can have is that you can have incoming current which is unpolarized, but an outgoing current which is completely polarized, because this is 0 up, 1 up. So these kinds of things can be done, and one could see whether such scenarios do happen. One can also look for disorder effects. If you assume that the disorder only happens between the closest disorder induced tunneling happens only when 2 like spins are close to each other. You don't want to have magnetic scattering. So only if they have the same spin they will scatter. Then in that case, if all of them are in phase A, then which is what you have when you have sharp edges, then there can be no scattering, disorder induced scattering, and in which case you will get, for instance, for this is a 2 quantum point contact geometry, and it's been tuned to the nu is equal to 1 plateau, and this will remain very sharp. On the other hand, if in the central region I change it to phase C, right, by changing the slope or the width of the how slowly it goes to the outside, then you find that if you have 2 like spins close to each other, in which case you can have a backscattering. There can be backscattering here, and so this nu is equal to 1 plateau, which is due to this red 0 up state, will get backscattered, and you will not get such a good plateau anymore. So you can have it will undermine the quality of the plateau. So you can have other signatures as well. I will mention one more, and actually we have written many other things in our paper. One can also get left-right asymmetry. If you have phase A on the left and phase C on the right, if the source is at the top left, then you will find that there is no possible backscattering over here. So you will measure this nu is equal to 1 plateau perfectly. On the other hand, if the source was at the bottom right, then you can have backscattering here, and this plateau will be degraded. So that's the main points that I wanted to make. I will now try to summarize what I have said and conclude. So what I emphasized was that integer quantum Hall effect states are topological states characterized by bulk topological numbers, which also determine the number and chirality of the edge states. But the actual structure of the edge states is subject to details and can be observed in appropriately designed devices. So we have focused on a regime where, as the confining potential is made shallower, the spin of the edge modes switch, bringing like spins closer to one another due to the exchange interaction. Our control parameters are the interaction strength, which is EC by omega c, and the edge smoothness parameter W by L. And we focused on the EC by omega is less than 2.5, where the bulk is actually partially polarized, because this is where we got interesting results. For small W by L, the order of the edges, as I said, followed the bulk order, which is phase A. For larger W by L, depending on values of EC by omega, we went to either phase B or phase C, which are both phases where the like spins were close to one another. Thus, where they gained exchange energy. And the crucial requirements to see this switching transition are a partially polarized bulk state, moderate to strong interaction strength, and a smooth edge. And what I also wanted to stress is that this is some different from what was been studied earlier, because no charge reorganization at all takes place here. So it's in a different class from earlier reconstructions. And we've also suggested some experimental scenarios to see this spin switching. So some of the things we haven't done and which we would still like to do in this area is that we have not looked at spin textures. For nu is equal to 3, bulk does not have spin textures. Nu is equal to 1 has spin textures, but one doesn't know what happens at the edge. And we have other thing which we are really interested in, we have not done is we have not looked at anything regarding this quantum Hall effect in graphene, where people have looked at things not at bulk, not at this long range Coulomb, but people have looked at other short range interactions and so on and looked at order of bulk. I guess what we have done should also generalize easily to the composite fermion picture, and nu is equal to 3/7, because what should happen at nu is 3 should carry over, but we have not looked at it. And we have also not looked at edge reconstruction in other topological phases. And what will happen when you put Coulomb interactions and other topological phases. I think Yuval has started doing some work on this, and this is something we plan to do.
If you have spin-off coupling, does
Yeah.
it give you something drastically different here? Because somehow potential will also
become spin-off. I don't know. I mean, I don't think people have started looking at this in detail yet.
But the G factor needs small, these are spin-off effect. No. There is.
Okay, that's it, I think. What happened is.
Yeah.
To understand the left-right asymmetry experimental proposal a little better, can you go to the next slide?
Yeah.
You said injecting the current from one corner and the other
Yeah.
corner.
From one corner to this corner, I'm thinking of source here and drain here.
Yeah.
And then what I was trying to say is that because this is upspin and this is a downspin,
Which is not.
we will not have scattering between the two. But on the other hand, if we had this other phase where this was upspin, this is also upspin, one up, then it was possible that you could have scattering over here, and so what will go through it to this side will be only a part of that.
So this will be putting contacts physically on the edge of the sun.
Edges of the sample.
And if I reverse the magnetic field, it will just be the opposite.
Yeah, that also is true. Yeah, it will be the other way around. Yeah.
Any other questions?
I guess this is probably an experiment, but putting contacts on the edges is something too straightforward.
It's not impossible. There are people who do point contact at the edges through tunnel barriers.
Yeah, I was saying that you can probably, they can individually contact each of these, right?
Individually contacting the channels, I don't know. Individually contacting very locally
At the point is
contact
possible, yeah. But I had
Looks like the channel that is not there.
I had heard that they can now individually contact channels. I don't know whether that's right.
But
They're not physically channels. Yeah, I agree. I understand. But yeah, these are pictures. They're not in that sense.
I don't know if there are matrix element issues which can be somehow. I don't know.
I don't know. What I know is done is there were some experiments trying to look at anti-reflections on the edge plate. So there you put a contact at the edge with a tunnel gradient. So that injects exactly at the corner
Of the edges.
So if there are no more questions, let's thank Sumathi.